Good morning, everybody. What I'm going to give is a light touch introduction to a few examples of structures analysis in the space context, ranging from coupled thermal, optical and structural analysis, standalone mechanical analysis, impact and explicit methods, right through to PCB reliability and composites assemblies. And then in one example, what I'll do, I'll go into a bit more detail in the steps involved in a CubeSat analysis. So as mentioned, I'm going to focus on the structures subset of the Ansys portfolio. So the subset I've highlighted here, ranging from mechanical, LS-Dyno, Sherlock, right through to design life. I'm also going to talk about how these products interact with the other physics solvers available. And I think that's a theme. So first, really, a bit more detail into the various structural products. So on the left here, we've got Ansys Mechanical. Now, this is perhaps the original and the core structural solver of the Ansys portfolio. And it provides an incredibly broad range of implicit static and transient analysis methods, some of which we'll touch on today. So it's capable of structural, thermal and vibration analysis, amongst many others, and has a really strong focus actually on providing coupled analysis methods with other solvers, which we'll also talk about. And then we've got the explicit solvers, so LS-Dyno and Ansys Explicit, which isn't shown here, it's part of the Ansys suite, and then Autodyne. Now these enable analysis of very highly non-linear scenarios, or events which sort of involve extreme degrees of deformation or significantly changing contact conditions, or which occur over short durations, explosive or hypervelocity events. And then LS-Dyno in particular also offers quite a strong baked-in multiphysics capability with fluid, electromagnetic and thermal solvers baked in. Now we've also got some more manufacturing-oriented products such as Ansys Forming for metal stamping, there's the additive solution for simulating additive manufacturing processes, and that in fact has been used to great effect in recent space applications. And then we've got Sherlock, which provides predictions for electronics hardware, so looking at thermal durability and vibrational durability of PCB assemblies, for example. And you see here we got ENCODE Design Life. Now that takes our structural predictions from mechanical and LS-Dyno and other codes, and it provides a fatigue and durability prediction capability. Durability is of particular importance in space where you've really got limited opportunity for in-service maintenance. And then finally, we've got Ansys Motion. Now that's an industry-leading multi-body dynamics solver for analyzing rigid and flexible bodies. And it's complementary to, and it does vastly extend the inbuilt rigid body dynamics capabilities within Ansys Mechanical. So really, you can see there, we've got a very full-featured suite for doing structural analysis. Now, clearly in space, the structural response to thermal loading is going to be of key importance, and this functionality is one of the primary analysis methods available in Ansys Mechanical. So we can represent the thermal properties of the various materials, things like the expansion coefficient, or the conduction, convection and radiance coefficients and capabilities. We can investigate how those thermal loads and heat transfer will affect the structural performance of our systems. Now, these materials data, they're available within materials databases within the Ansys suite. There is another product called Granta, which is a very full-featured and rich source of materials data. Or you may actually have your own bespoke properties, and ultimately you can input these, so things like your thermal expansion coefficients or your Young's modulus or Poisson's ratio of your materials. And what we want to do is we want to predict how these thermal and heat loading will affect the structural performance. So ranging from what you might consider as a straightforward differential expansion problem right through to utilizing things like the latent heat capabilities of wax solidification to provide cooling in heat pipe systems. And I mention that because it was done quite recently on the James Webb Telescope, so I have some level of knowledge of that. Now, in addition, you'll see I've mentioned IcePack here. Now, this touches on the coupling capabilities within the suite, and they're a massive focus within the Ansys environment. And IcePack, that enables a heat transfer solution using a CFD method of sort of circuitry within the satellite components. And this then predicts the conduction, convection, and radiation. And those resulting thermal loads are fed back into mechanical to provide thermal boundary conditions, and that enables the structural response to those thermal loads to be investigated. Thermal fatigue, for example, is of key importance in these structures where durability and reliability are absolutely paramount. So another example, actually, of the importance of inclusion of thermal effects is their effect on optical performance. Now, everything these days needs an acronym, so this is referred to as STOP, so Structural Thermal Optical Performance. And what you can see here, this is an example of an optical mechanism where the transient thermal analysis drives a transient structural analysis. And there's a link to SPIOS in there, which enables optical analysis. So you can see here we've got the transient thermal driving a transient structural, and we've got a SPIOS input there. And this system here, this is subjected to a 3-hour sun load, for example. And so the loading from that exposure to the sun can then interact, or we can generate the thermal loads. We can look at how that affects the deformation of the structure. And ultimately that's going to affect how the optics behave. So you can see that these Ansys multi-physics solutions they enable you to examine these effects in any combination really and get a really good prediction of what's going on. And it enables us to mitigate and eliminate reliability problems and design safe and effective products. You'll all know it's highly expensive, if not impossible, to replicate the operating conditions experienced in space using physical testing. And so analysis is really therefore essential to underwriting the performance of these assemblies, in this instance structurally, but as you'll see from my colleagues' subsequent presentations, electromagnetically and the fluid responses as well. So what I'd like to do now is run through a small case study on a CubeSat multiphysics solve. So as you can imagine, when we launch and then deploy these situations, we've got load conditions of highly fluctuating temperature, high and low pressure environments got to be considered. We've got a huge range of vibrational loading. But at all times, we've got to maintain the structural performance and reliability under all of those load conditions. And one way we can do that, we can set up what we see here. So this is a system of interacting analyses where we feed in our geometric configuration from an HFSS model. We put that into a transient thermal solve. And then the results, so the thermal solve then informs the static structural solve. And then what we can do here, we can get a prediction of the deformations and stresses and strains within the structure. And we can underwrite its performance. But in a similar vein, we know that the HFSS performance is going to be very much governed by the deployed shape of that antenna, that balloon is inflated. And so what we can do a structural solve to get the deformed shape of the antenna. And then this can inform an HFSS solution, which is going to give an idea of the electromagnetic performance of that antenna. So you can see this, it can be a very much a two-way process, these physics can strongly interact. But I do also want to highlight down at the bottom here that this has been done parametrically. So you can see what we're generating here is also what's called a response surface. And this gives an understanding of the strength of relationship between the structural response and various input variables like temperature change or geometric configuration. And this gives a fantastic understanding of the behavior of this system. And it really informs the engineers and scientists involved of which are the vital characteristics for safely and reliably deploying these satellites. So here we go. This is an idea of the output from the transient thermal analysis. So we've got a heat flux time history. We've got an idea of the emitted radiation. And what we see, ultimately, we get a prediction of the temperature distribution through the structure. And that temperature distribution is then fed into the static structural analysis, and we can predict the resulting deformation and actually the stress and strain distributions within the structure. So importantly, in this case, what we get an idea of the deformation of the antenna. And that deformed shape can then be fed back through to an HFSS simulation of that antenna response. But what you see here is that the nominal shape has a very different response to the deformed shape that we're predicting. So to have that deformed shape predicted and informing your HFSS solution is invaluable. But really, I just want to emphasize here, this has all been done within this pretty easy to set up environment. So in Ansys Workbench, where we can use these interacting physics and structural solves to then inform other solutions and vice versa. I've got another example here. This is a composite propellant tank. Again, we've got an acronym, PMD, so propellant management device. And this has to withstand high internal pressures, so in this case, 6,000 psi. But what I want to highlight here is this is a filament wound product. And so what we need to do is set up this analysis and have a look at how the fibers are distributed within that composite tank. And then ultimately, perhaps we might want to do a dynamic simulation of this, so to look at the modal, the shock, or the harmonics, and random vibration response. And Ansys Composites pre-post was used here to build this model. And what this does, this really does make the generation and the processing of these composite structures very, very straightforward. And I say that from personal experience of having set up a filament winding simulation in the past without tools like this. It's really quite challenging. It's tinged with a little sadness that I didn't have access to this 5 years ago, because it would have saved me an awful lot of time, because it really is a very good tool for setting up very complicated composites analyses. We can look at the structural response when we're deploying and assembling these systems. We need to deploy them. In this case, we've got solar panels reliably and with the opening sequences very closely controlled. We don't want things like excessive displacement from attitude control events. We've also got to withstand the thermal cycling within the whole life cycle. And we've got to withstand shock and impact loads during launch. So all of these different loading conditions can be built into our analysis systems, in this case, a Ansys mechanical environment. And it gives us an idea then of the sort of an understanding of the system modes of behavior. Thinking about a sort of totally different scale, really, we can also use the same thermal and structural analysis capabilities to look at the physical durability of circuitry, in this case of PCB assembly. And what we're doing here, we're solving this structural random vibration loading in mechanical. And then those data are fed through to a different software package called Sherlock, which is a specific tool for looking at reliability and durability of assemblies like these. And it's another great example of the sort of interaction of the systems where loading and conditions from one specialist solver are fed into another. And so we can get this rich analysis capability within one environment. And then we can even look at the other end of the spectrum, so explicit analysis. And we've got a couple of examples here where Ansys Mechanical and LS-DYNA were used to predict damage resulting from debris impact. I mean, be that the tragic foam debris impact on Columbia, right through to potential space debris impact damage on satellites. And these, as I mentioned earlier, the explicit solves are very much for the highly nonlinear, the sort of very short duration impact events, which is ideal here. It was used forensically in the left-hand case, but it can be used prescriptively in the right-hand case to mitigate the damage that you would get from impact events like this. And then really, no recent space webinar is going to be complete without some mention of the James Webb Telescope. And you'll see in this instance, the engineers, they used Ansys mechanical simulations to look at solutions to the precise mirror pointing as a sort of function of the natural vibrational frequencies of the structure. And mechanical really helped sort of determine the effects of having this connected segmented mirror. So the segments will respond to disturbances, in this case, in the same way that a monolithic mirror would, which is of critical importance. But again, this is coupled with Ansys ZMAX in this case to look at the complex optical behavior of the system and the sort of the numerous gold-plated mirror segments they've got. I mean, there's 18 segments in this primary mirror, all designed to function as a single mirror with a surface smoothness of about 100 nanometers. I mean, it's astonishing technology considering the loads involved and even just getting it to a deployed condition. So the engineers used ZMAX to sort of design and test every step of that alignment process, really from the initial segment search right to the final phasing. And I do recommend that those two links down at the bottom left there on NASA and Ansys blogs are really worth a read if you have time. They're easily readable and give a fantastic sort of in-depth description of how the James Webb Telescope was designed and how Ansys Mechanical helped out in that. So I do hope I've given a brief and I know it's a very top-level idea of the structural response and the structures side of things.